Hi, David Vizard here, and you are watching Powertec 10. Today's subject is tunnel ram intake manifold. Should they be used on the street? What do they take in the way of having the ability to produce manners for street work? Are they really only race only? Can you modify them? What can you do to them? And the list goes on. First off, I want to settle this race only deal, right? When a tunnel ram fails to make it for a street motor, it's because there's something wrong with the geometry or the specification of the engine, and that tunnel ram manifold does not suit that engine. That's just like putting the wrong two-plane manifold on or whatever, right? The biggest problem is having ports too big. The tunnel ram was initially designed as a drag race manifold, and the thing is the ports tend to be sized on the big side for top end power. Now this is okay if you use a manifold intended for a 350 say, and you now bolt it onto a 427 inch engine, it's probably going to be okay. But if the manifolds have the right intake size for the displacement and the RPM range and so on and so forth, they can work very well. My friend Andy Wood has got a truck with a tunnel ram intake manifold, and we tested this against a stock intake, a old tunnel ram manifold, and the new Holley tunnel ram manifold for a small block Chevy. Well, guess what? That manifold, well, both the tunnel rams work, but the latest one, straight out of the box, was 20 horsepower more than the one that I spent quite a time modifying. Anyway, the thing is we're going to look at Andy's video, and the deal will go along the bottom here as to where you can find it. But today we're going to look at what you can do to a tunnel ram intake manifold to make it work better yet. Well, I've moved the manifold to one of our 5 school downdraft porting benches. Students like these, they can keep their clothes clean, so when they go out for lunch there's no big shakedown on their clothes and all that. They're in perfect nick. But anyway, what we're going to do here is we are going to look at how the induction pulses from some cylinders can adversely affect the others. So that's what we'll do now. Stock Chevy small block firing order is 1843 65 72, which goes like this: 1 8, and it's the furthest away from 1 as it can be, so this induction pressure wave here has virtually no effect on this. 1 8 4. Now that's still a long way away, so this induction and that induction pulse don't interact very much. 3. So we get 1 8 4 3. You can see that the big pressure wave coming at one port can affect the other. And here's what happens. The second cylinder to draw has a big negative pulse come from the overlap period, from the exhaust extraction. So number 3 has a slight robbing effect on number 2. Right? It's small, it's like maybe 1 or 2%, but it is there. But let's go on. We've got 1 8 4 3 6, 5. So this situation is the same as this. 7 is next. So we got 1, 8, 4, 3, 6, 5, 7. This cylinder here robs this one, and it's quite badly. So we need to address that situation. Then we go from 7 to 2. Then it goes to 1. So it's not too bad with this gap between the two. But we really have to address this. Now, this particular engine is going to use a 4-7 swap. Here is the 4-7 swap, diagrammatically shown, right? Essentially what we've got here is, there's our stock firing order, and this is what we're going to change it to. Now, these arrows depict where it goes. Number 4 goes here where number 7 was, and number 7 goes to where number 4 was. You can't just do this with the timing, spark plug timing change. It has to be done with the camshaft. Now, the fact that it alters the arrangement of the firing order means that the intake manifold, in terms of the pressure waves, has to be done according to suit this firing order, not this one. So we'll look at that now. With the stock firing order, number 7 and 5 were in a robbing situation because they're only this far apart. So the pressure wave from 1 can start sucking charge from the other. That's 7 robs 5. Now, let's see how this works out with our new firing order. Let's just go through the sequence of events on our 4-7 firing swap. Right, here we go. 1, 8, and then instead of 4, it's now 7. Then it goes to 3, then 6, then 5, then 4, and then 2. So this cylinder wants to rob this one instead of this cylinder robbing this one. So we've moved the events. Now, I'm sure that most people don't take this into account. Now you'll notice it's 4 and 2 that fires together now. It's not fires together. Induction. Number 2 tends to rob number 4. Before, it was number 7 tending to rob number 5. So our intake manifold for a 4-7 swap needs to be slightly different. Maybe people are only getting a small change in power from this 4-7 swap because they are not catering for this. I don't know that to be a fact, but I suspect it may have something to do with it. Anyway, what do we do to cut down the robbing of one cylinder with the adjacent one? Well, here's what happens. Let's use the cylinders we're going to have to fix here. What happens is number 4 starts its induction stroke, and the biggest pulse, part of the pulse on the induction stroke, happens in the overlap period. So this cylinder starts to draw, right? Now, when it's 90 degrees down the bore, the pressure drop across the valve and in the port is less. So when this cylinder draws, there's this big negative pressure wave comes up here, and it expands out, and some of the charge that's going down there does this. I've exaggerated that. So what we've got to do is to try and cut that down, because this cylinder never regains that loss. This cylinder, on the other hand, has the benefit of the charge already moving in that roughly in that direction, right? But the two don't counteract each other. We're always at a loss on this cylinder greater than we pick up on this one. How do we fix it? Well, the first thing we do, the simple mod, is to make sure that this cylinder here can draw air from anywhere it wants easily. Whereas this one, we want to try and make it draw air from here the worst possible way it can. So what we do is we radius off this turn here so that we leave a knife edge on this side and a nice big radius on this side, so the air favors going down here. Now, to make up for this knife edge here, what we do is we expand it over here so that the pressure wave can start to fill this area and get diluted or diminished before it ever gets to here. So that's what we're going to do in the plenum. So I will show you the progress as we go. So why would we want to do a 4/7 swap? Well, there is supposedly some advantages in terms of crankshaft torsional vibrations. There's not, the peak vibrations are reportedly less on with this firing order, and there's supposed to be a small power gain. I've been told that numerous tests have shown that there's about a 1% gain in power. Now that's not very much, but let me point out to you, 1% here, 1% there, 1% somewhere else starts to add up. If we get a camshaft from Comp Cams, it costs us virtually nothing to get the 4/7 swap. So we might as well get it. And that will pay off so long as we have the right cam timing for it. We'll talk about that later. Here's your first move toward compensating for the robbing of cylinder 4/2. We grind this here so it's a generous radius all the way down here, and this basically is a sharp corner, or it will be really sharp by the time I emery it. Now you could just cutter it like this and it will work just fine. I need to make this look good because, well, I've got an audience watching, right? But that's where we go to start with. Next move is to work on this edge here and this edge here. A comparison of these ports and these ports should give you an idea of how much they've been reshaped. Of course, we're only going to do it on these ports here. Let me make a few points. Bring this back here. Don't round it off because we've got to do the top to match it. Right, so I'm not going to finish that quite yet, although we'll do an emery roll job on it. This here is a nice big radius, and I'm pulling it back here more than along here into this corner. Same with this here. I'm pulling this corner this way. Not too big a radius on there. I don't want it to affect that one. And we've got this knife edge here. Right, so now I'm going to emery that so that you can see what it looks like when it's polished up. Now I'm not going to use it in polished form, but it's easier to see the form of it because it reflects the light. Well, here's our port shaping up. You can probably see the general trend here. Once again, let me reiterate, we try to make these four edges favor this port. We're having this edge try not to favor this porch. Right, and get this right in a minute. But I've radiused this off here. Now, it's possible to put a bigger radius on, but be aware that a radius tends to damp the shock wave or the pressure wave that comes up the port. Now we want to damp this one, and we want to enhance the flow of this one, so it's a whole compromise deal. But this is what you should aim for. Here's a few points to note here. I'm kind of halfway through dressing the radii into the runners. This one is virtually finished, right? Notice a radius here, not a sharp edge. A sharp edge does not work because there is no time when these cylinders are drawing at the same time. So this cylinder needs as big a radius here when it draws as it can get. And this one here also needs it at a different time, so the compromise is just a radius. Anyway, a couple of points to note. First off, you see how I've dug this out here? This is so that we can have an end to the runner that's more well defined. I mean, we're limited, we can't do that here, but I've dug this out so that we can put a radius in there, and then there's a definite end to the runner. So that's that. Now notice that the radius on here is around about half an inch, maybe 5/16 or so. You do not want too big a radius, and I'll go into that later on. But right now I'm going to finish off these, and we're going to flow test this one on the head and see how much difference dressing this makes to having it stock. Oh, hi, you're back. I'm just finishing flow bench teardown here. Flowed this. It works good. I think I covered most everything before, but see how I exaggerated this corner here so that there was more a well-defined end to the port. Radius, they don't have to go all the way around. On this port I've done it, but here they're finishing off at about a 70-degree angle to this face. Right, this is the knife edge port. This port I've just finished flowing flowed less than 1 CFM less than no manifold. This one here flowed less than 1 CFM difference, and this one was about 3 in spite of that sharp edge. And that's mostly because all this round here is large. Now, a couple of points that I didn't raise earlier on, which I think I need to deal with, and these are: first point to note is that all of these techniques can be applied to a single 4-barrel manifold, right? At least where it's applicable, and that means the favoring of the cylinder being robbed in terms of flow generated at the plenum due to putting that sharp edge on to prevent the other one stealing from it. Now, the other thing we can do to that port is to make it smaller. This means that the port runs at a higher velocity, and that makes it harder for the other one to steal. On the dyno, we see this torque curve starts sooner, it makes a few more foot-pounds and a few more horsepower, and it carries on longer. There is no downside. All I've got to do now is finish off the porting on this with a fine tooth burr. We don't need to polish it. And then we'll take a look at the Plenum top. We'll talk about that and spacers to go on it. Well, here I've put in the streaming countersinks. Right, what this does is it stops or vastly reduces raw fuel running off these surfaces here into the ports. If the fuel is running, it gets into one of these countersink holes, which have just gone to the point where they've got the straight edge of the drill, right, so that there's a swirling motion there and the fuel gets reintroduced into the air. Anyway, that's about the last op. But let me show you the finish on the ports. Well, here we have the lid, or the top of our tunnel ram manifold, and I'm looking inside here and I don't see anything obvious that needs doing. I tried it out on the bench and it has almost no effect on airflow. It's still within the odd CFM of flowing what the bare port does. So the next step is to talk about spacers. Now, I had considered doing this on this video, and then I realized there is so much more to spacers than meets the eye that I'm going to do a separate video on it. Right, for now, all I need to tell you is that a 1-inch spacer on here works. That's all you need to know at this stage. But down the road, we're going to test a whole bunch of spacers, some designs I guarantee you will never have seen. Well, that about wraps up our tunnel ram modification video. But I want to say that this is not the complete, how shall I say, rundown on how to modify tunnel rams. There are intricacies which apply just to 1 or 2 different designs, and we'll have to get into that down the road when we do an engine build. But for now, what I want to say is, if you like this video, hit the like button. If you really liked it, hit the subscribe button. All of our likes and subscriptions to our channel will mean that we can do more in-depth and higher tech features on engines. Help us get to that goal. Thank you.